Homework 0 grades were sent out. If you didn't get homework 0 grade and you expected to get a homework 0 grade, send us email. Homework 2 I just posted. Some listed on Piazza, it's on the homework page. There's new skeleton code on the GitHub repository. Homework 1 peer reviews will go out today. Please start on those as soon as you can. And then get Cython installed and working for homework 2. You can still use the Cython test thing if you want to do that. If you haven't done it yet, then you're gonna make a frowny face from me. Hopefully you have. There's still a couple of people I think who are having trouble with that. I can talk to you after class. For the peer reviews, as I said last time, make sure that you're doing your comments in this tab of the pull requests that you get in the files changed, because that is where all the commits are stuck together in one file. And it'll be a lot easier for people to read through it. It'll be easier for you as well. Remember Wheaton's law. Search it if you need to. Basically, be nice, be useful, all those things. Your comments are public and they're not anonymous. By choice. So be nice. Be nice. We'll know who you are if you're not nice. We'll know who you are if you are nice, so we can give you kudos. All right, today, this is on. There's a part of homework 2 is based on, or you need to know this for part of homework 2. One of the problems, SIMD extensions within CPUs. This is also a nice stepping stone to GPU programming and understanding how GPUs work. SIMD extensions on CPUs started with MMX. You may have heard of MMX, SSE, SSE3, 3D now, et cetera, et cetera. AVX is the one that we're going to use, or emulations thereof. SIMD, for those of you who haven't heard it before, is single instruction, multiple data. So a bunch of tiny workers, the CPU, doing the same thing on a bunch of different data types. SIMD is, in CPUs is reasonably new and not the most common way to think about computing. You usually think about a value and another value, and I process them together in individual registers. In GPUs, everything is SIMD. You've got 1,000 tiny workers doing exactly the same thing. Anyway, in modern CPUs, we have special vector registers for doing this, particularly under the newest instruction sets, where you do something like, here are 4 floats. I treat them as basically as a value, as a package. They go through life together. I process them, I multiply them by some other set of 4 floats. I add those to some other 4 floats, and then I get 4 answers out, and maybe combine them at the end. But in general, they're just special multiple value registers to think about. They're not, what? You can write in a very high level language, right? Python or Rust or Go or OCaml or whatever. And it gets translated down into a serial program based on the sort of normal instruction stream that you think about, where you have just values and you can think about how those might map to registers. There isn't as much support for this sort of, for these SIMD instructions in higher level languages. You almost always have to drop down to something nearer to C. Compilers are getting better at this and are actually pretty good at this in a lot of cases in terms of finding places in your code where you're doing the same thing to a lot of similar values, where there are opportunities for SIMD optimization, but it's still not there entirely. So to take full advantage of it and to get the boost in power, you do have to drop down into a lower level language usually, or give very good hints to the compiler. So why SIMD? Why is this interesting? Why did this happen? Why do we have this? Any guesses? Why are they adding SIMD instructions to processors? Why don't we just do it in another core? You can also do it in another core. The why is the same graph as before. 2004 is also around the time that SIMD really, well, took off before then. But we started adding cores when the frequency stopped going up, when we still were getting more transistors. but basically when Moore's law started to die in terms of frequency scaling. So SIMD, more transistors, same clock speed. That's the regime that we're stuck in now and probably will be until we get better at physics or chip physics. A lot of increased demand for graphics and sound. Sorry, one moment. SIMD hardware is simple, right? I want to add two numbers. I want to add two numbers. I have that in my ALU, my arithmetic logic unit in my CPU. Now I want to add two sets of two numbers. I just put another adder right there next to it, right? It's not actually how it happens, but it's pretty easy, right? I'm like, I have a bunch of transistors. I need to do something with them. I could build another core, right? And then I have all these cache, crosstalk things. I have to make the core synchronize. All kinds of problems. If I'm like, I'm just going to make it so that it adds numbers better, I'll just add another adder. And then I want to do two more adders, right? It's very easy to dump transistors into more compute because this is very low-level compute, so I don't have to do a lot of scheduling tricks like that. It's not perfectly like that, but it's simpler to add more compute than to add another core. It's also efficient, partially because I make the programmer do everything, right? It's harder to use these, so I'll make you do it because you're smart. Cores can be efficient, right? And we'll see how hard that is to actually make that happen in this homework. But it's not as obvious. N parallel operations on n values, it's basically the same time for one value, right? If I just dump in more processing. And so I get almost perfect speed up very easily. Don't have to make a very complex addition to my chip. And I can give that power to people very, very directly.
What about in terms of power? You start adding more cores, does that require much more power?
It does. It's linear with the amount that you're doing there. And in fact, then it's going to use more. But if you look back, the power hasn't increased that much. Partly because when you make the chip smaller, you can use lower voltages, and the power goes as the voltage squared. Power ends up being pretty constant, though. It's not really too much of a problem. I mean, the power density as things get smaller is a problem. But in general, it's still pretty efficient. So the history. MMX was the first of these. MMX doesn't stand for anything. It's just like MMX. They've tried to stick some things on there later on, and there was even a lawsuit by AMD against Intel about whether or not MMX could be trademarked, because if it's an acronym, then no, and if it isn't an acronym, then yes, and anyway. MMX was not a great thing. It had 8 64-bit registers, like 8 times 64-bit registers, and then you could break those up, but they were integer only, and you couldn't use them at the same time you're doing floating point math. They overlapped with the floating point registers, so it was either I can do integers fast or floating point, and I can't do floating point fast, and I can't do both. And so they were sort of this that made no one happy. But then they fixed it up just a few years later with SSE. You got 8 128-bit registers, you could break those up into various pieces. And then in 2001, they doubled the number of registers with SSE2, and then there's a big gap here, right? We'll come back to that. And then now we're starting with AVX. So we have 16 256-bit registers available down at the run. Just to understand how large can your working set be before this becomes inefficient? Because now we're also talking about, if we're talking about moving around 256 bits, right? That's 4 cache lines. So if we're going outside of 16 pieces in our working set in what we use regularly, then we're pushing that farther away from the chip, right? We can keep 16 values, or 16 packed, multiple valued registers together in the chip at once. You start doing something where you've got a computation that involves thousands of these, you're back to pushing a lot of memory around. They may not help you that much. All right, and coming up in the future, near future, 32 512-bit extensions. Okay, what happened in 2004? Back to the graph. 2004. Let's put it all in. Right, let's stop for a while. Let's just add cores. All right, so there's this reset there. I think is what happened. They started pushing out more cores, and the complexity there of the chip design meant that they spent some time working on multi-core systems, and then they're like, okay, now we can go back to improving SSE and that stuff. So there was a pause, but now just looking at what they're doing now, what they're doing in the near future, and what they plan for these SIMD extensions, they're going to push more into there for a while, at least for the next few years. I would say at least 2 more iterations, maybe 3, of pushing more into these basically multiple value, these SIMD instructions. So they're very powerful in a lot of cases. All right. If you do end up actually working with SIMD in the future and need to write portable code, I'm sorry. It's going to be a pain. These are all the possible, like, there's a processor for each of these. Some processors have some of these. Usually if you're, if you have AVX, then your processor probably has everything that points back, but not always. And some of these are Athlon or are AMD only, some are Intel only, some are IBM. So if you want to take advantage of them, you'll have to learn this hierarchy. You don't need to know it for this class. I just wanted to show you how complex this is. Like, people are like, oh, this is great. I'll add this, I'll add this. I'll add this one instruction and make something totally incompatible with what everyone else has done. Or only people who have this exact processor can take advantage of this in very limited cases. Chip design is a horrible, horrible thing. So this graph is a little tricky to read, but it's important to understand, why do we care, right? This is just another technology. There are a bunch of technologies out there to choose from. This is basically, you look at the peak performance that you can get from a processor in terms of flops. And that's over here. Double precision flops, starting way back at the 387, basically 1 million, up to 100 billion. Yellow is what we got from just frequency scaling, right? And that ends in around 2004, 2005. Just make the chips faster. So for a long time, all our performance increases for double precision math were just coming from, make it faster. Just make the chip faster. And then you get things like, all right, well, we need to do something better. We need to start doing these deep pipelines on the modern architectures where we start executing the next instruction before the last instruction is finished. And this is very common. That started around here and goes right there, the dark orange. Basically, as soon as we started doing that, we got the full benefit, and it hasn't really increased that much. Right, and then we have things like multi-core and superscalar and things like that. The blue there, the light blue, is what we're talking about today. And it looks small, right? But there are 2 things to notice. One, that's a log scale. And so that's almost a full step of 10. That's basically 8-way parallelism in single instructions. And so it's worth 8 times. That little step compared to everything here, yeah, it's not as much as what we've got in the past, but everything here was in the glory days, right, where we could just make it smaller, make it faster. Now we have to do work. And so we're getting basically 8 times improvement, right, from a single core, just for using SIMD. All right, so it's significant. And it's going to get, as we add, as we double the size of these registers, these SIMD registers, each time we double them, we get twice as much performance, basically. It doesn't take, if we're multiplying 8 floats or 16 floats in one of these, it takes the same amount of time. So it's a very easy way now to get a quick boost in performance. And so and especially if you're doing scientific computing, this can be quite useful. All right, how do we use these? We're going to concentrate just on one version. We're going to talk about AVX. 256 bits, so we have either 4 64-bit doubles or 8 32-bit floats. Or 16-bit floats, or we can do integers and these other stuff and whatever. But we're just going to talk about floats for the most part. All right, and we just have 8 values in parallel in a register. How do we use those? How do we create these? How do we program with these? In homework 2, if you've already, if you dug into the AVX stuff that was in the Cython test, you might have seen some of it. There's a more complete example with some documentation in homework 2. But we'll talk about it here just so that you're familiar with it beforehand. All right, are there questions before I start talking about instructions and C code and stuff like that? Questions so far? Totally clear? No, it's just the sort of most. It's recent, but not so recent that we don't expect. I mean, most people should have it. I mean, so everything since about 2013, probably around then. Not always. You can emulate them, at least some of the instructions, just in SSE. You just take twice as many registers, something like that. But it's more just we're trying to hit, we could use AVX 512, but very few people have that. Okay. That's the basic reason. We're not going to use anything really complex. You can get some very complex instructions in here, and some of them are limited to AVX or AVX 512. But if we're just talking about, let's just do some math, this is a good place to start.
What's an example of a more complex instruction? Like could be useful for scientific?
Oh, yeah. Oh, yes. These are almost always very useful for scientific computing, simulation, graphics, sound processing, DSP type stuff. I'll post a link on Piazza later. Remind me if I forget, which I will. That shows you've got a big table of all the different SIMD intrinsics. There are many. Some of them are very complex and confusing why you would want them. There are things like add, basically in the even registers. There are ones like in the even registers, add two, take two of these values, sum them in the even registers, and subtract them in the odd registers. You're like, why? That's a fast Fourier transform step for some, or maybe discrete Fourier transform. There are things like that where it's like, this is obviously tuned to one particular problem. They added it because they found that it would make it very fast for some large number of applications. All right. This is a very simple AVX function. It looks, if you look at it and just ignore and it's kind of noisy, right? I don't like working with this code because every operation has, this prefix, what you're actually doing, and then a bunch of stuff about types. But this is basically, I'm gonna just pass them in as variables, as if they were integers, right? You've got a vector of values. You just treat them like an integer or a pointer. You don't even have to, not even as a pointer, you don't expose the internals. You just pass them around as if they were integers and do stuff. So for example, I'm gonna make a constant 10. It's just 8 copies of 10.0. And then I'm gonna multiply a by 10, just using the multiply operator, and I just get back an M256, right? The compiler is responsible for then figuring out where to stick this and store this. And then I can add that to another one and just return it, right? You don't have to do any, if I were doing vector math, if I were trying to implement this in C as, here's a collection of 8 values, I'd have to be doing allocation and passing them around. And I could use structures to get around it, but really it's pretty simple. It's just that it's really ugly. The wrapper we've provided in homework 2 makes it a little cleaner, right? So those are the types, right? It's just M256. It's an opaque sort of thing. And then all the operations operate on, you tell them what's actually in there using this postfix. Packed, single. The other options are packed D, PD, packed double. And then you can do scalar operations, which actually operate just on, usually, the 0th entry. So you can have, you might see if you'd go digging into this into code like this, SD or SS. But generally, we're just gonna use the packed versions because those are the interesting ones, and probably just singles because we're not doing high performance, super accurate double precision math. All right, we're gonna use, in this class, and for most of the work you might use these for, you probably only really need a small subset. Right? You probably mostly just need these. You can certainly do all the homework with these because that's how we've given you. If you wanna wrap another one, that's fine. And it's pretty obvious how to do that within the homework. Again, really noisy. That's what we're actually talking about, okay? Add values, subtract values. The obvious ones, square root, and then some that are not obvious, right? and on floating points, creation, comparison, and then this move mask function, which is poorly named. So how do you create these values, right? If you start with floats, set one and set, create a value. Set one, you copy a single value across. We've already seen that in the earlier example. And then you can set them from pass in 8 floats. There's also one where you can go to memory. It's a little tricky because it has to be aligned, so not gonna talk about that here because I don't want to talk about memory alignment and stuff like that. It is important to know that value 0, when you do this, ends up at the least significant bit, or the least significant element of the register, and val 7 at the most significant bit, because when then you pull them out later, you'll want to know where they are. Oh, sorry, set should probably just be called create. Set, so it takes in that value, I should have given a type, is just a float. So val, on set 1, val is a single float, and it gives you 8 copies of that float as a M256. And then set, the more general case, you pass in 8 floats, and it packs them together into a register and gives you that register back. All right. It means so you have 2 possible orders that they could end up in. When you actually pull them back out, you need to know which one is where, right? So one of the easiest ways to do that is cast it to a take its address, cast it to a pointer, and then you're gonna read them off as floats. Turn it into a float pointer instead, right? Then you need to know what order you're going to see them in. If you put them in there, what order do you get them back out when you then go one at a time? So least significant in this case means lowest memory address when you do that. And I should verify that, actually. That's what the documentation said, that documentation versus implementation. It's pretty easy to test, right? Cast it to a float and read it out.
So it puts one in each register.
It puts one, well, it puts one in each register.
Or it backs them all into one.
It packs them all into, so when I say register, I mean this 256-bit monstrosity. So there's only one of those. It contains 8 values. And in this case, it contains 8 values that are 8 floats. And they're just right next to each other. Okay? And then I can manipulate those independently. Okay, clear? Comparisons are a little tricky. There are a lot of operations you can do here if you dig into this. Basically, you give 2 registers and an operation. And the operations are also ugly in terms of what they're named. But to parse it, to understand what's going on, operation always will be compare, then how you're actually comparing, equal, less than, greater than equal. And then 2 letters. OR-U for ordered or unordered. That's what happens when you compare to NaN. Which do you return, true or false? And I can never remember. I always have to test. I always put in a U and say, okay, did I get what I expected? And compare to a NaN. Did I get what I expected? No, switch it. All right, now I'm good. And the other one is quieter signaling. Signaling indicates if you compare to NaN, then it's an error. If either of them contains a NaN. You almost always just want to use quiet, probably, maybe. It's basically, can you detect when there's a not a number value? Everyone familiar with NaN, not a number? 1.0 over 0 is not a number. Doesn't know what to do, so it uses a special representation. Okay. How do you use the comparisons? So the results of the comparisons are, again, you've compared 8 values to 8 values. You need to store 8 values worth of results. True is all ones across the however many bits you have, 32, 16, 64, which happens to be negative NaN. Anything, so we have to talk about floating point representation. Aren't you excited? This is how floating point numbers are stored in IEEE. You have a sign bit, you have the exponent, and then you have the fraction. The fraction is assumed to start with 1, I think. In any case, anything that has all ones here is a nan. Doesn't matter what's here or over here. Anything where the exponent is all ones is considered not a number. Which means you have a whole bunch of not a numbers to choose from. Negative nan is important because the sign bit later will be able to use that. All right. How am I supposed to use this? What makes sense if I... Oh, so, yes. So floating point numbers internally uses a representation not unlike scientific notation. So 1.03 is represented as, whoa, that's not a square. It's like my hand had a mini stroke. So the sign bit, 0, okay? And then the mantissa, basically, since I'm in the 0 to, it's binary, but I'm less than 2. So the mantissa, let's do actually 2.03. The exponent here would be 0.0001, right? So that's 2 to the 1 times, and then whatever, basically 2.03 over 2. Actually, I might be wrong about that. It might have to be a 2 here. But it's 2 to the first times some fractional value such that I get back to this, right? So this is just raised to the binary power. Actually, there's a sign bit in here too. So you can have smaller values. And then some fraction that you multiply together, just the binary representation of that number times this to get to the closest value we can get here. The Wikipedia page is not bad on this, and that's where this image is from, okay? We won't have to do much more than just, really, for this, all you need to know is what the comparison does. That it's gonna spit out all ones or all zeros. And if you pull those out as values, as floating point values, this is what you'll see, 0 or negative nan. But generally, you don't actually do that.
This is like the 16-bit number that's stored in each register.
Yep, yep.
So
This is,
are we assuming 8 registers?
you can assume 8 here, I mean, or however many you have. So you're gonna do a bunch of independent comparisons, right? And then in each block of 16, you'll get one of these two values. Okay, so you'll get all ones where it was true and all zeros where it was false. Make sense?
If you had many more registers, would it be slower to computation?
If I had many more registers, would it be slower to perform computation?
Not necessarily the same thing.
Oh.
Is it that people don't have more registers just because it's more expensive?
So why don't we just have more registers in general? Yes, registers are expensive. It's also a gating problem, right? Or wires problem, right? I've got a core of compute, and I've got registers somewhere, and all of them need to get to the compute in one cycle, 0 cycles, really. They have to be always available. So the more I get, the more I have, the harder it is maybe to move those around. Particularly if I'm gonna be, if any instruction can fetch any register. Since they have to be so fast, they also tend to be more complex and more sensitive to physical limits, right? Or what? It's sort of an optimization problem. Do I add more registers? Do I add more L1? Do I add more compute? Do I add more SIMD instructions? Do I put it in L2? Do I try to make a better branch predictor or a better out of order? Right, there are all these places you can put transistors in a chip. And it's sort of driven by, well, we'll try this and see what it works. I mean, I'm sure that Intel and AMD both have plenty of simulations to argue for different settings. This seems to be one of the optimal ones right now, particularly for the sort of compute that people actually do, as well as scientists and academics, but real people. So it's more just sort of demand-driven. These instructions have been found useful, and so people are dumping it in here. Would it be slower if we added just more registers, or if we had more SIMD registers? General compute probably wouldn't be affected. They're going to tend to sit over to the side. Would it be, are you asking if SIMD instructions would be slower? More generally, I mean, the effect might be, so did I answer your question? It's sort of an optimization, right? And this one is found to work very well, to the point that there are several iterations planned to expand these. But there's also, you know, how maybe it could be we just haven't explored the right paths. But in general, there are limits that are pushing in different directions, or well, limits and demands. All right, we can get all ones or all zeros. How do we use that? We have an AND operation. It's bitwise, right? So now we can turn things on and off where we need to, right? If I have two SIMD registers and I AND them together, I get bitwise AND. If all -1 and all 0 in one of the registers, now I've masked off the true, right? Or I could do a NOT. There's a NOT operation I think is just bitwise. So basically I can do a comparison and I can just choose the values from one side. For example, maybe I want to take a maximum, although there is a max instruction, or I want to do some sort of computation where I only want to operate where the where a certain condition is true. I test for that condition, I do the compute, and then I just put the value back only where I've got the mask. And then I can use an OR to combine that with what was there before, or something like this. You can also then, at some point, you may want to actually know what the status was of this comparison. You can use this move mask, which just extracts the high bits, and so it's kind of poorly named. It basically pulls out the high bits and gives them back to you as an integer value, like a regular integer, just like one you can work with. So you can get back the high bits as 8 0 1s. So again, if you're working with comparison, it gives you the sign. So if you got negative NaN, you get 1 where it was true. First questions? It was a lot, maybe.
Yeah, I didn't get it at all.
Sorry.
Okay.
So the comparison, right, puts zeros or ones. So now if I have an AND operation, and or comparison does, right, and puts it in another 8-valued register, another SIMD register.
Okay.
And
ones or zeros.
only ones or zeros everywhere. And so now if I have bitwise operators, I can turn off computation for certain paths or do computation only on certain values, right? Maybe I only want to operate on values that are above some threshold. I put that threshold in one register, and I compare. Anything that's above that threshold, now I compare to find where the values are high, and maybe I want to do something to those values, right? So
Within the floating point bits?
Above that, within the register itself. So now I can basically use the bitwise AND or NOT, whatever, to say, okay, do something.
You can select something.
Right, it's a selection tool. It's basically do something and then use this mask to extract the values that are of use to me. So is that part clear, right? It's basically, I can turn off parts of the computation or extract parts of the values.
And what do you mean by where true minus NaN?
Yeah. So I don't know what that's not English at all. So if it's all minus, oh, you know what this is, I had a bug earlier.
Is it if they're the same?
Ignore that line, it makes no sense. It should be if all minus NaN and 0, right? Then it's a mask where true, right? That's not minus, it should be -1, it should be minus NaN. Basically, if minus NaN, then it's basically a mask when I AND this. So masks is a verb talking about the AND operation. I need like a sentence diagram there. Basically, you can use it to mask off values is what I'm trying to say. Okay. All right. So this one allows you to turn on and off different parts of computation, take advantage of these comparisons and do different things based on that. And then you can get back to some high-level control. How many values were above the threshold using this move mask, and then count the bits. Or just check if any were, right? Check if anything passed the test. And that's it. That's enough to go off and make your programs 8 times faster, right? Depending on what you're doing. If you're doing numeric computation, if you're doing, especially if you're doing something like dot products or matrix multiply or something like that, super fast, right? Especially if you break up your computation into little blocks of 8, you get an 8 times speed improvement, okay? It's coming up soon. Sorry. It's the sign bit for each of the 8 values, right? So let's pretend like I only have 4, right? So if I have 3 minus 2.2, 1, and minus nan, no, let's not do that, minus 4, right? If I have these 3 values and I call move mask, I will get back 0, 1, 0, 1, so 5, right, equals 5. Equal 5? Good. Right, does that make sense? So the sign bit on a positive number is 0. And then the negatives, I get back the 1s. The minus nan will also give me that back, too. Does that make sense? I mean, you'll get back 8 bits if you're doing, when you do move mask, you'll put PS or PD to tell you how to interpret it. And that'll tell you that's how many bits you get back. But you get it back just as an integer, basically packing these bits together. Why do we care about that integer? Well, so at some point you may want to say how many of these values are positive. And this gives you can use, or just are any of these values positive, right? Or negative, or true, if we're talking about we just did a comparison. Any, some, we can do, we can count the bits, or we can just use it as is it equal to 255? None of them. All of them. Okay. And this is where that LSB, MSB, or low memory, high memory also matters. Again, I've tried to, I think I put the documentation correct in homework tube. I'm gonna test it just to make sure about what order you get these back, right? Because we have these in some order and we created them in some order. I wanna make sure that when you check, which value was which, that's the order you get here. No, it just comes back. Well, yeah. You might need to do some bitwise ANDing to figure out which one in particular, if you care. Yeah, so then you might do, I think it actually comes back maybe this one goes there and this one goes there, depending on how you write this. But yeah, if you care about individual values, or you care about how many were true, then you've got, there are fast ways. There's a pop count instruction actually in most architectures. Any architecture that has AVX has pop count, I think, yeah? And that tells you how many bits are true in a single instruction. There are other ways, but a lot of time you'll just use it as, are all the values above some threshold, am I done, right? Or below some threshold, am I done? So you'll just use it as a 0-1 test, or 0 not 0 test. I want to put some code up for that, actually, to make sure that we do it right. Because I don't want to, I've been reading through the documentation and my brain is full of underscores and letters. So I'll do some examples using the AVX stuff that we handed out in homework too. And that'll make sure that I'm not lying. I'm also concerned about, so I know that you're one of the people that your computer needs that emulation. Right, so it's actually dropping down to SSE. And so I don't trust that. I mean, Intel wrote the header, but they're hardware people, so we'll check. It should be correct, but I want to make sure. Okay, more questions? You'll get a chance to work with this in one of the homework assignments. It's fun. Or one of the homework problems. All right. Like I said, they're iterating these, all right? Next one out, starting maybe this year or maybe chips next year, AVX512, double the size, double the number, so 4 times as much compute power, essentially, for a single instruction. It's starting to really put pressure on GPUs from below, right? Can we do, can the CPU do as well as a GPU in a lot of cases? It's getting close. This will lead into the next lecture, where we see, GPUs are when this metastasizes.
So in this description, like, is this adjusting the amount, like, for instance, in our example, we have 4 registers or 8 registers. Is this we're gonna have 32 registers, I guess.
Yeah, so this is on the chip. So in the AVX, a chip that says AVX inside or whatever, will have 16 128-bit registers. So if you're doing assembly programming, which hopefully you're not, or else you've made horrible mistakes. I mean, you could be a scientist that really needs it to go fast. If you're doing assembly and you're managing registers allocations, you have 16 to work from. And they're 120 bits. AVX512, for each core, or for each thread, will have 32 of them, so twice as many, and twice as wide. So if you consider so you get twice as much computation, right? That's basically what they're saying. Twice as much computation because it's twice as wide. Right, because if you put in a SIMD register, or a SIMD register of a certain size, you're saying you can do this many floats in parallel in the same cost as one.
Okay.
So when they double the width, they double the compute.
There's an ALU or something for each one of these registers?
Yep.
Okay.
Yep, exactly. There's a bunch of little parallel ALUs.
Are they ALUs specifically, or are there other?
There's other stuff. In general, it's going to be just in general, it's just an ALU or something, or approximations. They sometimes share hardware, and so the delay before an operation, the latency can be a little higher on some of these than you would expect from a multiply, but it's close. And I think in general, it's the same as the scalar single value version. Increasing the number of registers just makes it a lot easier to take advantage of these, right? You're not going to have to eject values out of registers nearly as often. So that will probably not, 32, 64. 64 is about as many registers you have in most CPUs. So that might double again, but it's just going to get wider for at least a couple more iterations, I think. And it's a nice, cheap way of saying, if you're doing something that's really dense computationally, if you're doing graphics, you're doing sound, here, twice as much compute, boom, one iteration.
So, just you can fit 4 distorted images in one of these, and do that kind of in parallel, and you can have that straight.
Yes. Yes.
So that you can only do 4 in parallel.
Yeah. Wait, did it?
Or
Sorry, those numbers should be the same, 512, but yes, yeah. So you could see, 8 64-bit, 16 32-bit, 32-bit, or single bit, so 32-bit integers, 32-bit floats.
yeah, so it's only parallel within the same register, but
Yes,
different registers.
right, correct. It's only parallel within that single register, so the pairs of registers. The operations you do there, everything happens still. There are instructions that work with just one and and also ones that do things between them, like shuffle type operations within a register. I'm not going to talk about those. They're available though. So each register does it, yes, each register executes at the same time. When you do an operation, when you multiply, they go into parallel ALUs and get a parallel answer out. I hope I've made you interested in these. They are pretty fun. I mean, they're, admittedly, you can also screw up like 8 times at the same time, so it's way more efficient for your bugs. But they're cool. All right, coming up, we'll step from this to GPUs, which, like I said, it's like when these start to eat themselves. I thought a review on Wednesday, perhaps, after you've had some time to look at homework too. I see nods. Okay, we'll plan on that. So I will prompt you on Monday to post questions for that review, or you can start posting them now. So look at homework 2, look at the problems, think about what you're going to have to do and what makes sense and what doesn't. Friday, we're gonna have a guest lecturer who's gonna give an intro to Odyssey. We'll have a couple of quick examples there to make, we're gonna use Odyssey to make sure you have access to GPUs. If you have access to a GPU, you may not need this. If you already have done the intro to Odyssey, which some of you will do on Monday as well, may still be worth it because we'll run through some examples here, making sure that OpenCL, the environment on Odyssey is set up correctly for you. Yes? Do I still have GPUs available? You mean in my office, sitting there? What's that? Oh, the Jetsons. I do. No one has asked for one of these. It's not going to be your optimal. I mean, you can use it as a desktop. It's kind of, you can hook up to a monitor and keyboard and stuff like this. I do. I have 5 of these, and I'm saving them for final projects or whatever. They're very cool. The Jetson TK1, if you want to search for this, it's an NVIDIA. It's like a Raspberry Pi with a GPU glued on there, so it does like 300 gigaflops or something. And it's got nice connections for cameras and USB and stuff, whatever. So it can do like real time. It's what they use for, it's based on what they'd use for car control in the, I forget who collaborates with NVIDIA. Some car has GPUs in the back, so you can game and drive at the same time or something. You think I'm joking, but that's what self-driving cars are all about. Anyway, I have 5 of these, maybe 6, and I'm willing to loan them out. I would love for them to be used for projects. Look at what people have done with them. Justin TK1, there are a bunch of examples. We'll be doing GPU programming. They have OpenCL, they have OpenCV, the computer vision library. They're very fun. So let me know. It's gonna be first come, first serve. Or if you come up with a present, if a lot of people want them, then I'll do it by coolness factor. So propose something. But I'll loan them out for now, if people need them. All right, any other questions, yes? Does the GPU have to be a particular type? No, if it supports OpenCL, you're generally good, NVIDIA. If they support CUDA, they support OpenCL, yes. OpenCL also just runs on CPU, so you'll be able to do all the work in OpenCL. You should be able to. It's just that you won't be able to do any of the GPU experiments to see what sort of performance you get, or understand what's going on in the memory. Anything else? All right, look at homework 2 soon, because we'll do the review on Wednesday. So if you have questions.
We've done everything we need for
Homework what?
We've done everything we need for homework 2.
You should, yep. It's gonna be Python threading, some Python threading. I said you wouldn't do this, but we decided to do it for one problem. OpenMP threading in Python, and then an AVX problem with that. Okay? Is it long? You have till November 2nd. You can use that time as you will. And again, automatic 2 days of lateness allowed for every homework, and for some reason we only have 3 homeworks, so if you can add 2 to November 2nd. But is it long? I don't know. It shouldn't be as bad as Spark, because you won't be fighting with AWS is my hope, right? AWS added a lot of extra pain there and slowness, unfortunately. No, there's one more homework. There'll be one more homework on OpenCL and GPUs.